Yeah, I'm running out
It's
of,
a joke.
because my computer has quite little space.
This meeting is
So
being recorded. Fuck, Zoom just notified
yeah.
me. So annoying.
Okay. So hi everyone. Yeah, I want to keep it as a semi-informal discussion as well. So at any point, if you have any questions, you can always just stop me. Yeah, and yeah, I'm also trying to learn through teaching. So I don't know everything about quantum field theory. I don't think anybody does.
Everyone must refer to him by Professor Tan today.
And yeah, okay. So for prerequisites, okay, let me just give you an overview of what I think about quantum computing in general. For quantum computing, there's sorry, what am I saying? Quantum field theory, QFT. There's there are, for at least for the introductory quantum field theory, there's two main paths that um uh most textbooks or lecturers will go by. One is the canonical quantization method, and one is the path integral quantization. The thing is that the path integral method is it gets you very quickly, very easily to, it's kind of easy to derive Feynman diagrams. It's easy to reach Feynman diagrams. And that's, I mean, Feynman diagrams are like, they're kind of they are a hallmark of QFT. Yeah. You see it
I think
everywhere, QFT.
it was probably a better word for that because it like follows directly.
Mm.
Is that what you mean?
Uh, yeah, kind of. It
Okay.
reaches it's very easy to derive Feynman diagrams from path integral formulation.
Right.
Whereas for canonical quantization, you need to go through quite a few steps before you can even reach calculation of scattering amplitude. So in some sense, canonical quantization is a bit more involved. Yeah. So do you need to go through processes like you learn about the S matrix, and then you need to learn about the LSD reduction formula, and then you also need to learn about Wick's theorem before um before reaching Feynman diagrams. So the path is a bit longer. Personally, when I first started out, I actually started. I read QFT for the gifted amateur. I'll just abbreviate it GA, gifted amateur, by Lancaster, and primarily he starts introducing it via the canonical method. Whereas for Anthony Z, right, QFT in a nutshell, by Anthony Z, he kind of brings you along the ride with path integrals. And in David Tong's words, Anthony Z makes QFT look easy because he tells you a lot of lies. So the main thing is, the important thing to know about QFT is that it's actually still an area that's under research. So in some sense, there's no there's no one correct way to go about it. In fact, some of the formulations actually, when you go to a higher level, they actually kind of contradict each other. So often in practice, right, physicists usually use path integral as some sort of guiding principle where they can derive some relations from the path integral, but they don't really consider it rigorous. They and using inspiration from the path integral, yeah, I think that's the right word. They draw inspiration from the path integral formulations. They look at the equations that pop out of it, and then they try to use canonical methods to prove the things the ideas that they have from the path integral method. So yeah, so for this set of lectures, I'm going to try to go into both of them at the same time, because on one hand, I want you guys to be able to enjoy reaching Feynman diagrams and being able to feel like you're doing calculations, QFT calculations, uh, almost immediately. And then on the other hand, I also want you guys to know that there's the canonical method, which is the slightly more formal, slightly more textbook method. Yeah. Okay. So I'm just going to run through the prerequisites really quickly. Uh, for special relativity, there's the main postulate is that events in space-time are separated by they have an invariant two events in space-time. They have an invariant space-time interval, which is this formula over here, and one can read off the metric from it. And yeah, and that's so the metric is here, and the metric, you can invert the metric. So the metric over here it can be interpreted as a matrix. And whenever you have a matrix, you can take you can write the inverse. And we write the inverse with the upper indices instead of the lower indices. And it conveniently forms, it plays well with the index notation. Yeah. Okay, yeah, question?
Yeah, hi, Prof. I have a question. Is metric the same thing? Are we talking about the same thing as a metric in a metric space? Is that the same idea?
Yes.
Okay,
Yes,
cool.
actually.
Thanks.
Yeah.
That makes it much easier to understand.
Okay, great. Yeah, so when in special relativity, we ask the question of, because it's a postulate that this space-time interval is invariant, right, in all coordinate systems. We want to find what are the coordinate transformations that leave this space-time metric, this space-time interval invariant, and turns out to be the Poincare group, which is the Lorentz transformations plus space-time translations. Interesting enough, we won't go much into detail at the moment, but if you do representation theory on this Poincare group, you actually get spinors. You actually get this, basically get a lot of particles that you see in
This is
nature.
pretty cool.
You get spinors, you get vector fields, and yeah, and all this is covered in Steven Weinberg's book. So Steven Weinberg's QFT book is a book that is more for research QFT. If you want to do research in QFT, so in some sense, it's a more advanced QFT book. And in his first chapter, he talks quite a lot about the representations of the Poincare group. And you actually get, the nice thing is that you actually basically, by studying representation theory of Poincare group, you actually get all the particles. So yeah. Okay, so Lorentz transformations, when they act on position, like this, right? Lorentz transformations they are matrix with 4x4 matrix, and then your positions are 4x1 column vectors. So acting like that, you get a 4x1 column vector. And similar to how we constructed previously we had the Minkowski metric, right? And then we constructed the inverse metric. We can construct the inverse Lorentz transformation in a similar way. I put some details in the appendix, but in essence, the upshot is that what I want you to know from this special relativity prerequisites section is to just know that often we'll say that a theory is relativistically invariant, and basically what it amounts to is that indices make sense. So Lorentz covariance is when your indices make sense. So these follow the Einstein summation convention. I won't go into it in too much detail. There are nice videos out there. I can send the link to. But yeah, essentially Lorentz covariance, when you want to form a relativistically invariant theory, when you form a Lorentz covariant theory, right, both of them are synonymous, all it amounts to is that you must write the theory in such a way that the indices match. So in this case, the alpha is a contracted index, right? So there's a sum over alpha. And alpha goes from 0 to 3. And then beta is a free index, meaning that it must appear on both sides, and they must have the same position, meaning it's upper or lower. So indices can be the upper indices, right? When you have something, it can be either upper index or lower index. And they must be either both upper on the same side. So you see over here that beta, right, is a free index. Both of them are upper indices. And whenever you have a contraction, right, it must be a contraction between the lower one and the upper one. And if you satisfy these indices rules, then from the above discussion, it naturally means that your theory is Lorentz covariant. Yeah. Okay.
Prof,
Yeah,
can I
so
clarify what's the meaning of the upper and lower indices? Like, what's the physical meaning?
okay, so the meaning is actually is actually what kind of tensor it is. So okay, this goes a bit into, actually when we start to get the full picture, right? it's actually under general relativity, or differential geometry. So the upper index means that the upper index is known as a vector, and the lower index is known as a covector. Right. So often when there's upper index, we call it a contravariant index, and when it's a lower index, we call it a covariant index. So what physical significance is there? It is that if you have for the covector, right, when you have a lower index, then when you go from a frame, when you Lorentz, so you have two frames, right? One of them is a rest frame, and then one of them is a boosted frame that is moving around. So we know that the position would change by the Lorentz transformation. So the position is a vector, and all other vectors, right? All other vectors would transform in the same way as how the position transforms. Whereas if you have a low index, they'll transform by the inverse Lorentz transformation, meaning that the physical significance is that when you boost from one frame into another frame, right, the index, whether it's lower or upper, would tell you whether that quantity changes by inverse Lorentz transformation or a normal Lorentz transformation. Yeah, okay.
Okay, thank you.
And the nice thing is that to elaborate a bit more, right, the nice thing is that if you have a lower index and an upper index and you contract them like this, meaning that you sum over that index, then this quantity is actually Lorentz invariant. Which means that because you see that if we take this quantity and we boost it into the second frame, the moving frame, then A transforms with the inverse and V transforms with the Lorentz transformation. And when you have an inverse multiplied by the inverse matrix multiplied by the Lorentz matrix, you get the identity matrix. So such quantities are Lorentz invariant. Yeah. So you can build Lorentz invariance quantities just by looking at the indices. Yeah. So yeah, we don't really need to deal with all the Lorentz transformations individually, right? In field theory, in classical field theory, by just looking at the index, it's enough information to tell us whether what quantities, how the quantities transform under Lorentz transformations, and by extension, right, whether an equation is Lorentz covariant or whether a quantity is Lorentz invariant. Okay, yeah, good question. And okay, if not, let me move on. So that's for special relativity. The main takeaway is that we look at the indices. Yeah, we deal with the indices when we want to form Lorentz invariant theories. Okay, then for Lagrangian mechanics, so we have Newtonian mechanics, it tells Ff equals ma, right? Then we can also, there's a principle of an alternative formulation is the principle of least action, which can be shown to be equivalent, which can be shown to lead to the same results as F equals ma. You can derive F equals ma from this principle of least action. And what it tells us is that basically, if you want to move if a particle is going from a point A to a point B, it's going to take the path of least action. So it's going to kind of, beforehand, yeah, it essentially, in the background, it kind of has walked all the paths and has chosen the one of least action. And I mean, it's quite a remarkable principle if you think about it. But yeah, this will come in later when we talk about the path integral as well. So basically, I won't go too much into detail. I think you can see there's a lot of resources online about it already. You can get the Euler to find the principle of least, to find the path of least action. You can show that it amounts to solving the Euler-Lagrange equations. And it applies for so the Euler-Lagrange equations is a set of differential equations for every degree of freedom Q. So for example, if our system had coordinates r and theta, right? Let's say it was a pendulum, a spring pendulum with a mass m, then r is the distance to the fixed point and theta is the angle, then you there's two equations. So it'd be like that over the theta dot dt, theta dot equal to 0, and the same thing for r. Okay. It will solve for every degree of freedom q. What this extends to classical field theory as well. So the thing about the Lagrangian mechanics is that the action principle can be generalized to all of theory or all of physics. In some sense, all of physics actually uses the action principle. So Newtonian mechanics can only be applied to within the like it's just classical mechanics, but the action principle applies to almost all of physics. Yeah. So, yeah. Question.
Oh yeah, sorry. What does EOM stand for?
Sorry. Oh.
What does EOM stand for?
Oh, EOM stands for equations of motion.
Ah, okay. So,
I think I didn't
thanks.
mention that. Yeah. Good question. So so if we extend it to classical field theory, then you get the same thing. So you can think of the field phi. Previously, we had the coordinates r, we had the coordinates q, right? Qi, which could be r and theta, or like x and y. Basically everything, basically every coordinate is kind of like a real number. Every quantity, every degree of freedom is a real number. But what happens when you have a field? You have a field. A field is something that takes a point in space and spits out some value. Perhaps if you're talking about a scalar field, then it's a real number. And that means that at every location x, right, phi of x is a degree of freedom. So the Euler-Lagrange equations is of the similar form, except you see the indices is also yeah, just that there's indices now that is summed over in the Euler in the Einstein summation convention, and this equation becomes a equation for phi, and it becomes a field equation, meaning that it holds at every point in space. Okay, something I want to point out over here is that we see that this partial derivative has a lower index. This is short form for partial with respect to x mu. Okay, so if you one can actually show that this partial derivative transforms like a covector. Right? Even though it's x mu over here, the mu is in the upper index of x, but when you put in a denominator, one can show that it transforms like a covector. So likewise, when you have mu over here in the lower index, right, when it's in the denominator, then this entire thing is essentially, it transforms like a vector. So in the end, when this is in the lower index in the denominator, it's essentially like an upper index. And then that's why you can contract this lower index with this upper index. These are just some things to note. Yeah. So another valid way to write the equation of motion would be something like that. Yeah. Okay. So something to take note for the indices. Any questions at this point in time? Okay. If not, then
Great.
I'll...
Okay. So can we say that if we think about classical field theory, then the Euler-Lagrange equation always have infinite number of degrees of freedom?
Yeah, in some sense, yes. It's infinite degrees of freedom. Yeah.
Okay, then like how do we solve this kind of infinite sets?
Okay, so how do we solve? So let's illustrate that with an example. So for example, if the Lagrangian being this, then the Euler-Lagrange equations would yield this equation. So this is a field. This is the Klein-Gordon equation in quantum mechanics, and essentially this is the differential equation. It's a wave equation, right? For the field phi. So it's just like this is kind of like, I mean, the Maxwell equation is also a wave equation. So it becomes a wave equation. And when you have to solve a wave equation, you need the initial conditions, right, at the initial time. So you need phi of t equals to 0, you need the initial condition, and because in this case it's the second derivative, you also need the time, the derivatives of phi at the initial time t equals to 0. Okay, does that answer your question? So for
Okay.
classical field theory, the equations of motion, it amounts to a wave equation. The Euler-Lagrange equations give you a wave equation.
Okay, thanks.
Can I ask a quick question?
Yeah, sure.
Is your field necessarily like a fully continuous or like not really?
That's a good question. We honestly don't, as physicists, we actually don't really think much about that.
Oh right, I forgot you just assume everything is infinitely differentiable.
Yeah, I
Okay.
think in this case everything is more actually to be honest, to be more precise, because we have fields that look like the Dirac delta.
Yeah.
We have fields that look
not a
like the
function.
Dirac delta also. So it perhaps maybe to answer your question, right? Our fields are distributions.
Right.
Yeah,
But not
okay.
necessary. So like, do we just assume they're continuous by default, or like, is that not a allowed assumption?
Yeah, we take derivatives freely.
Okay, so we just assume it's differentiable. Cool.
Yeah. Let me see. Okay, so how I do who wants me to go through the going from this step right to this step?
Honestly, I kind of want to see that.
You want to see? Who wants me to go through raise hand? If more than 2 people raise hand, I would do it. Okay, sure. Okay, let me step through it, because this is admittedly something that something that I kind of struggled with when I was studying classical field theory, because textbooks usually just go from here to here, and then I'm kind of lost usually. Okay, so we have the Lagrangian. Okay, let me just pull up a better okay, no. Okay, I'll just work with this. So the Lagrangian is half this plus half m squared this. Okay, and this part is actually, we do the summation in the actual space-time coordinates is this, and then you have gradient because phi is a scalar field. Yeah, you have a question? Think here? Or is it just nothing?
No, but can I clarify, like, why the partial derivative have both a upper and lower indices here?
Oh, okay, good
Like in
question.
the first line.
In this case, so just now I defined the partial derivative as this, right? Which is basically a tuple of 4. So you have x, I'll just write blah blah. Okay, you get this definition, this one, for the
Yes.
definition for the lower index. So then for the upper index, for this one is it goes back to classical it goes back to special relativity, where we have over here we have the metric. The metric is a diagonal 1 minus 1 minus 1 minus 1. Then the inverse metric is also the diagonal. So this is the metric. If we take the inverse of this, we actually get the same thing, only for this metric choice. And this metric basically allows us to lower and raise indices. So if we have a contravariant index like that, which means that if we have a vector like that, right, a vector, then we can actually a vector is just a column of 4 numbers, right?
No.
In this case, it is t, x, y, z for the position vector. then we can actually apply this matrix to it. So we can do this and do a summation over the mu index, right? Because the mu is a repeated index by Einstein's summation convention. We sum over it. And this would give us oh, sorry, this is bad. Okay, if it's the upper index over here, then to contract it with another index, we need to use the lower index. So it's a lower index. Then that will give us x of mu. So yeah, so in terms of when you write it in terms of indices, is the derivative going back over here. The derivative with the mu in the upper index is just the contraction like that with this. And if we actually carry out the contraction, we'll see that partial over t remains unchanged, but the nabla, the gradient operator for the spatial part picks up a negative sign. Okay.
I see.
Yeah. So to be more explicit, this means that if I expand this term out, then it will look like so it's a contraction, right? So if I do the first one and the second one, the first one will equal to partial t. This one is a vector. The first one is a, so I split into two, right? This one is a vector, so it's okay, I'll just write it out. Dx dy dz. The first item is a vector. And the second part, right? This part in the box is a covector. So it is this. Yeah. Okay. Covector.
Wait,
Yeah.
no, sorry, that became a lot clearer when you wrote that.
Okay, great. And so if we do the sum over, so you see that the index is summed over, right? The mu index is implicit is summed over from indices 0 to 3. Then it is a dot product between is essentially a dot product between 1 and 2, which will give us this expansion. Okay. All right.
I see. Thanks.
Okay, no problem. Yeah. Okay, so that's for that. Okay, so continuing. So if I take the partial derivative with respect to, oh man, I should really expand the canvas size. Page data. A3 manage custom sizes. Apologies. Let me just
This really feels like a real lecture now. I think you need to click on add, yeah. Then just like scale it up to crazy.
okay, so now wait, that didn't really help. Sorry, I used to have let me see if I have one of those. Let me see, I have one of those pictures, documents. I used to have a bunch of templates that that are quite big. I think they are in pictures. Sorry for the technical things. Sorry to pictures. Oh gosh, it's gone. That's why it's let me see. I have a blank PDF as well. Let me just use the blank PDF. Okay, yeah. Okay, this should be better. You should give us more space. Okay, sorry. So so we had our Lagrangian, right? And there's half partial t squared minus this squared plus m squared y squared. Okay, so our partial derivative of L with respect to this one, right? So what I'm trying to evaluate now is this term over here. I'm trying to evaluate partial L over partial mu, but remember mu is something that goes, mu is an index that goes from 0 to 4, sorry, 0 to 3. So I need to evaluate it. I need to evaluate four of these guys. I need to evaluate and so on for y and z as well. Okay, so for this one, it will just be the 2 goes down, just be this, correct? And then for the y and z, right? One is just it's actually minus of that, and for the y is also likewise. So what I can deduce is that for the nabla, it's actually minus the gradient of phi. Everyone clear so far? Okay, great.
Yes.
Okay. And what can I actually deduce from this? I can actually write it in a more compact form, that the lower index, right? This is actually just this. Because remember the upper index, right? The lower index had derivatives with respect to t and then nabla. And then the upper one was the upper one was defined by the contraction with the Minkowski metric of this. Correct? So from these two, they are derived manually, very manually by going each coordinate at a time, right? I actually can write it in a more compact form. Everyone clear? Anyone lost?
This is just like a notational convenience.
Yeah, so it's a
Ah,
notational convenience.
Got
indeed.
it.
But what's nice about it is that you can actually so most textbooks, they will just they write the Lagrangian in this form, and then they'll say that we take the partial derivative and then they arrive at this form. This is I've just gone through the very detailed step of substituting each coordinate in, right? Mu equals to 0, mu equals to 1, mu equals to 2, mu equals to 3, and then seeing that it is in fact correct. Yeah. Because yeah, it's not immediately clear from initially looking at this, right? How we can take the partial derivative. Like one might, if we try to take the derivative, so we have this term. I mean, something that I used to ask myself a lot was, if we have this thing, right, and we take the partial derivative of this thing with respect to this, doesn't it look like, doesn't just look like, you see, this thing is it's like your
Fixed
depend.
fraction.
Yeah, then isn't it just this term? Shouldn't it be half of this? Right? Why do I not get the half over here? So this is in fact correct. This is actually wrong. And the answer is that the answer is that actually to actually do that, right, we need to actually get the correct answer by using the index notation. We actually need to consider this as a contraction of this with mu and nu, with Minkowski stuff. So now both of them have lower indices, and this is safely just a constant, and the half is also just a constant. And from here, then I can apply the product rule. So product rule, remember these are indices. So if I differentiate this one, okay, so if I expand it out fully, right, it's actually a summation over mu and nu, because mu and nu are summed over, and each one of them goes from 0 to 3. And then it's half of mu this and nu this. And then I take the partial derivative with respect to like this, and then if you expand it out, yeah, you end up getting this. Or rather you end up getting, wait, sorry, I forgot to contract it. you end up getting this. Which gives you this. Yeah, so I think this index notation thing is not so clear. When in doubt, you can always just go back into the substituting in the mu equals to 0 and to 3. Okay, yeah. Yeah, question?
The partial, is that a partial of the two, like the first side? It looks like a partial, but I'm not sure.
Which one? Oh,
The box thing on the right side. Like, is that
on the
true?
right.
Yeah.
Oh,
that's a
this is a
partial, right?
partial. It's a partial.
Okay,
Yeah.
right.
Okay, yeah. So anyway, yeah, if not, let me just continue. So so if we take the so we have evaluated the partial derivative with respect to this, and then so that's our this term over here, which we just derived in great detail. Then we remember we take the derivative of that, we contract it. So these are contracted indices. This will give you a wave equation, and this is actually known as a Klein-Gordon equation, which is a relativistic equation for scalar, or rather spin zero particles. It's a spin zero equation. So something nice about this is that we can expand phi in terms of whenever we have such an equation where we take derivatives of it, it is convenient to express that field in terms of in Fourier space. And the reason is because if you substitute this relation into here, if we take the derivative, let's say we take dt of phi, right, and we substitute this Fourier expansion into it, then the k dot x over here is the k dot x is expanded as omega t minus k as a spatial vector dot x as a spatial vector. So in the exponential, it'll be minus I e I. It'll be minus I. You take the partial derivative with respect to t, it'll be minus I omega e minus I k dot x phi of k, and then this one integrated over the full momentum. And this term, right, we see that if we have another partial t over here, that just amounts to this thing being squared. So at the end of it, you get omega k squared, and then the spatial thing, it kind of follows. And this, you arrive at this, which is known as the relativistic energy. We arrive at this, which is known as the dispersion relation for relativistic particles. And if you multiply h bar squared on both sides, you actually get this. So we often make the identification that E equals to, this is one of the one of the formulas that we learn in high school physics, equals to hf, which expressed in terms of omega is this, and then at the same time P equals to h bar k. And so substituting, if we multiply h bar squared on both sides, right, we roughly speaking, we get this. Okay, so this class scalar field theory, it kind of recovers the relativistic equation, the relativistic energy relation for scalar particles. And yeah, question.
So what's phi tilde again?
Phi tilde.
Like
Phi
in the-
tilde.
yeah.
Phi tilde is the components of this scalar field in momentum space. So one way to think about it is that when you have a vector, you can express it in terms of coordinates, right? In terms of components, right? But these components depend on the basis. So you can expand it in terms of the x, y, z basis.
Oh, okay, cool.
Right? Yeah, or you can express it in terms of some rotated basis. So one way to think about Fourier analysis is that when you think about Fourier analysis, you're actually just expanding in terms of these are the basis vectors, and these are the components. And this integral is just a sum. Yeah. So that's one useful way to think about Fourier analysis, actually. Yeah.
Definitely not sum.
Okay, so Okay, so why we're talking about classical field theory is because when we want to talk about canonical quantization, in canonical quantization, okay, so let me just write it here a bit. If I have a field phi and I express it in terms of Fourier modes, so this is a scalar field. I can express it in terms of Fourier mode. Let me call the Fourier modes AK, and then if I want if my phi, okay, there's also the complex conjugated one. If it's a real field, then this one must be the complex conjugate of this. But in general, right, it could be, if it's a complex field, then these two could be independent functions of K. Okay, I'll just let it be, in this case, complex conjugated. So this is a real field. I'm talking about real scalar field. If this is a Fourier expansion, right, in terms of Fourier modes, it turns out that after the process of canonical quantization, which I'll go into greater detail in the next lecture, but after canonical quantization, these coefficients of in the Fourier expansion, they actually become operators. So they actually become, you know, in quantum harmonic oscillator, the QHO, we have the raising and lowering operators, right? And then they commute, they have a commutation relation. And one can show that when they commute the energy, they get like basically themselves, or when you commute it with the energy, you get minus A. And then you get a ladder of states. You get a ladder of states, one being the ground state. And then if you act on it with the raising operator, you get a next excited state, which you call the one state. And then if you act on it twice on the ground state, you get the two state. And one can show that the energy applied on each state, right, n is something like h bar omega n plus half. So each of these states are eigenstates of the Hamiltonian, and by acting on them with these raising operators, you get higher and higher energy states. So it turns out that these Fourier coefficients, they actually become raising and lowering operators. So what that means is that you know, when you have, if you have a string, right, a string, just a classical string with two ends tied to the things, then you get a bunch of oscillation modes, right? You get a bunch of oscillatory modes. Each mode can be shown to be essentially independent, blind to the other modes. So each mode has its own equation of motion, and the total waveform will be a linear combination of all the modes, and each of the mode is basically living its own world. It doesn't interact with the other modes. So likewise, right, in the real scalar field, each of these modes are independent modes. They evolve independently, and each of these modes are quantum harmonic oscillators. So I'll talk about this in greater detail, but I just want to give you a small small bit of foresight when they actually become this A and A star actually become operators, and I use the hat over here denotes that they are operators acting on some Hilbert space. Yeah, and that's what we call the Fock space in canonical quantization. Okay.
Oh my god, that's a meme.
Yeah, any questions so far? Okay, so yeah.
Wait, sorry, pause. The M here, are we integrating over M? Like we are integrating over the M, like is M a contour there on the left side?
On the left,
Oh wait. We haven't
is
moved on to
mass.
this yet. Have we moved on to this already?
Sorry?
Have we gotten to equation 22 yet? Or are we still
22, oh no, not yet.
Oh, okay, sorry. Yeah. My bad.
M is just a mass actually, M.
No, it's
I
like that
you're
one.
talking about
The
this
weird
M.
math cal M, yeah.
Oh, that M is just denoting a manifold. Yeah.
Okay.
Integrating
We are
over
integrating.
manifold.
I'll let you speak first. Sorry. Yeah.
In this case, I'm just gonna let manifold M be R13 Minkowski space. But when we get to more interesting quantum field theories, we can actually talk about quantum field theory on a torus. Or quantum field theories on more like a cylinder. You can do compactification on a cylinder where essentially you say the two ends of the infinities, they must have the same field values. So essentially, if you're two infinities, right, if they must have the same field values, then if they're equal, then essentially they're saying the field lives on a circle. And if that's your spatial direction, your circle is a spatial, your circle is your spatial manifold, then time, right? Time is just the real axis, then S1 cross the real number line gives you a cylinder. Yeah, I leave it over here. I write M because in general we could be talking about quantum field theories, but I just put it there as a convention. Yeah, actually I can just remove it also for the purpose of this. Okay, so just now we saw that when we have just this Lagrangian, this is known as the free Lagrangian, because there's no interaction terms between phi. Yeah, you only have phi squared. Phi squared terms, the coefficient of phi squared terms gives you a mass. Yeah, and interaction. So this is a free theory, but if we add terms like phi cubed, right, or 5 to the 4, 5 to the 4 is particularly famous, particularly popular as an introductory example, and we actually talk about it soon. Phi cubed is the one of the simplest theories that start to demonstrate asymptotic freedom. Asymptotic freedom is something in QCD where it basically tells you that your quarks cannot be too far apart. If not, the gluons would come in and form antiparticle pairs. Yeah, but at the moment we have a free theory. If I add, so I have a free part, what if I add on this J phi term? That's known as a source term. J being, in electromagnetism, you have J being the current. So yeah, if you add on a source term, then your equation of motion become this, right? Because on the right hand side, when you take the partial derivative with respect to phi, you have the m squared phi, and then you have the j term. Yeah. So yeah, you get this extra thing. And this is actually very similar to if you see Maxwell's equations, you also have some you also have something in terms of something, and then on the right hand side, like Laplace equation, right? Laplace equation is just this. I think there's a minus sign. Is there a minus sign? Something like that, right? This is where we put our charges, right? This is where we put our charges, and then we can think of the phi as a response to the charges, and phi, we must solve this equation to know exactly how phi is, how the charges have what kind of field the phi is as a result of putting the charges there. So likewise, J is our source, is the source of our field phi. Yeah, in the free theory, it could be in the field theory, it just has many modes. Okay, so now we're actually getting to a very interesting part where how do we solve such equations? Okay, so that brings us to Green's functions. I think I'm going to skip over time evolution for now because I want to go to Green's functions. Okay, so Green functions. A huge part of quantum field theory is propagators. This is where we start to get to the fun calculations, but previously it was all just the prerequisites. Yeah, sorry, it took up almost an hour. Yeah, I hope you guys weren't too bored by that. Okay, so the fun starts when we talk about propagators, because propagators and QFT are some really fun stuff. Propagators have go by many names. One of them is Green's function. One of them, they can be calculated using path integrals, right? They can be calculated using complex analysis. And more importantly, right, when we have a Feynman diagram like that, let's say we have scattering of 2 electrons using the photon field, all these lines are actually propagators. And this entire equation, this entire Feynman diagram is actually equivalent to a particular integral of some of the propagators, right? Propagator, and then this will be propagator, and then along with some exponentials. So by understanding propagators, we'll be able to understand part of our Feynman diagrams already. Right? So mathematically speaking, what are propagators? What they're green functions, and what are Green's functions? It's a technique to solve differential equations. So if we have electromagnetism, in this case, we're working in the Lorentz gauge. So the gauge A it comes from, if you guys, I'm not sure, you guys can check out this equation. Yeah, just search electromagnetism gauge theory. And essentially it boils, this is Maxwell's equations in the Lorentz gauge. We see that there's a very repetitive structure, right? Some nabla squared, and then these constants, and then partial derivative squared over the time equals to something, some source terms over here, some source terms. And essentially, if we manage to solve a general form for this, a general ODE like that, then that answers our electromagnetism questions for all functions. So now the thing is that I give you this equation, right? I give you some specified function h, which is how my source terms behave, rho and j. And now I want you to solve for my f, right? I want you to find the function f that satisfies this thing. Okay, so there's so many h that I can give you. For all you know, I can give you h equals to x squared. I can give h to x cubed. There's so many h. How do you even start tackling this problem? What is nice about it is that if we notice that this has the form of ax equals to b, in linear algebra, I give you a matrix A. I give you a matrix A, and I want you to find some column vector x that you don't know, and I give you the things on the right. This is a linear equation. If I give you 2x minus 3y equals to 5, and let's say x plus y equals to 2, this is of this form, ax equals to b. So in this case, I give you the b on the right-hand side. I give you the differential operator. I give you the so-called matrix A. I want you to find this f. You can see the parallels with it, right? What's cool is that we can, so essentially, what do we do in linear algebra? In linear algebra, we just find the inverse of the matrix A, and now whatever b comes along, whatever b I give you, you just apply A inverse on both sides. So I have ax equals to b. I apply A on both sides on the left side. Yeah, question.
Okay. Is A always going to be invertible?
Yeah, that's a good question. So
like
in linear,
it's not going to be invertible if it's not from general linear of your, like the general linear group.
Yeah. I'll come to that, because now we're trying to invert a differential operator, and certainly some differential operators have kernels, have non-trivial kernels, right? Meaning that there are functions f that satisfy LF equals to 0. And if that's the case, then even if I get some solution x, right, and some part of, if I get some solution f, okay, if I get some solution f that satisfies AF equals to h, and let's say I have another k that AK equals to 0, then f is not the unique solution. I could have f plus k also, right? AF plus k would give me h as well. So for now, this differential operator, I believe this differential operator is invertible, but there are going to be cases where it is not invertible. Yeah, and those cases, it actually gives, there's some deeper connection with gauge theory, which I'm not super sure of the details at the moment. But I know I'm pretty sure Z mentions it in his QFT book somewhere. Yeah, I think when you try to do this method on electromagnetism, it fails or something. Yeah. Good question. Ken? Does that answer your question?
Yeah, it does.
Yeah. So so if you apply A on both sides, and you must apply on the left-hand side because matrices might not commute, right? So then this A inverse A gives you the identity matrix, and that solves your X for you. So now the goal is we want to find something akin to the inverse of this differential operator. But what does that even mean? So that's known as the Green's function. The Green's function satisfies this property over here, where the Dirac delta, right, is a function that is 0 except when, so this thing is 0 if X is not 0, and is 1 if X is equals to 0. Yeah, roughly speaking, yeah. So this on the right hand side, you can see that when we're going to invert a matrix A, right, we want the right hand side to be an identity matrix. Yeah, we want the right hand side to be an identity matrix. So A inverse is identity matrix. In this case, the right hand side is our identity sort of element, right, under the integration. I'll show you later. And L is our differential operator A, right? And the Green's function is essentially our inverse A inverse. So okay, so if we have this equation and we substitute it, okay, so I claim, right? I claim this is a claim. I claim that if we have this differential equation, and let's say I found the functions g that satisfies this identity, then I claim that my solution f can be found as an integral, right, of this source function that you give me, together with the Green's function. And so to prove that, going to the next slide, to prove that, right, if I just substitute in the definition of f, I should have L over here. Yeah, LF equals to L of, I just substitute in the definition. The L goes into the integrals. It skips along H because the integral, because H is, the parameters of H are X prime and T prime. They are not that, whereas the L over here acts on X and T. So they skip past H and they act on the Green's function, which has parameters X and T. And this one equals to this, because we define Green's functions as such. And if I then see this integral, right, we see that this thing is going to be 0 except when X equals to X prime. And this thing is going to be 0 except when T equals to T prime. And that basically means that when we integrate over this, X prime and T prime is only going to select the values of X prime and T prime that are equals to X and T respectively. And basically Dirac delta functions, or not functions, Dirac delta, they're actually distributions in mathematics. They're actually distributions, to be specific. Dirac delta distributions, they basically help you collapse your integral into yeah, they basically help you eliminate an integral. Yeah, so you see that H of X prime and T prime just becomes H of X and T. Any questions? Should I go? Am I going too slowly?
I just like to ask a question about the homomorphism. Sorry, not homomorphism, but the kernel part.
Yeah.
So like the unique solution only exists where you're like, if you have if your kernel is trivial, then the homomorphism is injective, right? So then you can get it.
Yes.
But is it like it doesn't have to be isomorphism necessarily, right?
Isomorphism from
like I know like what because like never mind, it's fine. I think that's fine. I think it's injective is good enough, honestly. We don't actually need isomorphism. Thanks.
Okay, sure.
I also
okay.
apologize for that question.
It's fine. There's no dumb questions. Okay, so okay, awesome. So we see that if we have this G, right, then I'm not afraid of whatever H you throw me. Wait, sorry, do you guys know about Green's functions? Am I going too slowly? Any yeah, just let me know if you guys want me to go a bit faster. So if I found my G, right, then whatever H you throw me, I can easily find my F, right? Yeah, my F is just given in terms of this expression over here. But of course I need to do the integrals. But the question is now, what is this g that I can, how do I obtain this magical g, this Green's function? And the answer is that in the case of the electromagnetism case, right, we can actually arrive at an expression for g in terms of when we convert it into Fourier space. So Dirac deltas, when expressed in Fourier space, they are essentially the complex exponential e to the power I kx, and this one likewise, right, omega t. And so the Green's function, if I substitute these two into the right hand side over here, yeah, okay, I substitute these two into the right hand side. But how about for g? The Green's function, I express it in terms of Fourier space, and these are coefficients which I do not know yet. I don't know them yet. I'm going to solve for them later. Okay, so I substitute the Dirac deltas into the right hand side and the g into the left hand side, and I get, so the left hand side, right, is equal to this. If you see that the derivative over here and the derivative over here, they pass by the k and the omega with no problem, this one with no problem, and then they hit this part, and then they hit and they stop, because when they hit these guys, they stop because there is an x and there is a t in here, so they cannot just walk past it like nobody business. So they see it, and now nabla, right, x on this x over here in exponential, and there's a I over here, so it x twice, so it's I, and then the coefficient over here is k, ik squared gives you minus k squared. Okay, and k squared as a vector means k dot k. And likewise, when I hit it with this on this guy, okay, this is just 1 over c squared. So I hit it with that, and then see this minus sign turn into positive sign. Yeah, so basically it becomes this. So that's a nice thing about Fourier space. Whenever you have derivatives, it's always useful to go to Fourier space, because when in Fourier space, right, your derivatives just turn into variables that you integrate over. That's the key idea of Fourier analysis. Okay, so that's great at all. So I have so this thing, this expression that I have yeah, so I've this, okay. And then if we compare equation 89 with these two, right, substituted into the original part, if I multiply them out, we see that I need this part to be equal to 1 in order for LG to equals to the Dirac delta. I need this part to equal to 1, and that means that this guy is just the reciprocal of this term. Yeah, the 1 over 2 pi to the 4 is just for these factors of pi over here. Usually when we do Fourier space, usually they come together with the things that we integrate over. Yeah. Okay, so now it just becomes this g of we've successfully found the Fourier transformed Green's function. Right, now all that remains is just to plug it back into the original integral. So I've plugged in the g of omega and k. And now I just need to, in order to find the real space Green's functions, I just need to evaluate this integral. Okay, great, awesome. It seems like our work is done, but this is actually where the interesting part starts. We see that if we integrate k, right, over omega, or rather when we integrate, let's first focus on the omega integral first, okay? Let's first focus on the omega integral. Now integrate over omega, k is k squared. I hit a problem when omega is k plus minus kc, because then the denominator is 0. And this is not even a well-defined function that omega is to kc plus minus kc, because it's not defined, because the denominator is 0. So how do I integrate over it? This is where Hadamard regularization comes in. And basically, what is Hadamard regularization is a method to regularization is a method of regularizing divergent integrals. And what does regularizing divergent integrals mean? It means that I am assigning a meaningful value to divergent integrals. And in fact, we actually see regularization pop up all over the place in math. You might have known the famous identity. Okay, it's minus 1 over 12.
This is
right?
not true.
Yes, it's not true indeed.
No,
Because
this is only if you plug it zeta of -1, that is defined as -112.
exactly. So this thing, right, it doesn't make sense because actually the left-hand side doesn't converge. So in terms of analysis, the left-hand side doesn't have a well-defined sum. However, Ramanujan, this guy, he found a way to assign -1 over 12 to this divergent, to this not divergent, to this non-convergent, yes, divergent, yeah, to this divergent sum. And he assigned it -1 over 12, and it's not just any Tom, Dick, Harry number they assigned to it. It's actually a meaningful value that when you play around, when you use this value for this sum in other parts of mathematics, it actually plays in nicely in some sense. And one of the ways he did it was to define the Riemann zeta function. Yeah, which he did analytic continuation on. So he defined the Riemann zeta function, which he did analytic continuation, which is a way of okay, I sorry if I digress, but I think this is too interesting to not talk about. So yeah, so how do you do analytic continuation? You know that when you express, let's have a function, I have a function, right? And let's say it's a real function. If I pick a point and I take the derivatives of this function at a point, higher and higher order derivatives, let's say the function is smooth, then I can construct polynomials that start to hug this, start to essentially hug this and approximate approximate this smooth function as I go higher and higher in terms of the orders for the derivatives. So the Taylor expansion, right? Taylor expansion, if I bring the order to higher and higher orders, it better approximates the thing. However, this doesn't always work, because if I have a function like, let me think of a function. If I've ordered a function like 1 over x squared minus 1, right? And let's say so if I plot this function, what does this function look like? 1 over x squared minus 1 is always, for big values of x squared, is near 0. It looks something like that, right? Yeah. If you Taylor expand this around x equals to 0, so Taylor expand
This is undefined at x equals to 1.
around x equals to 0, right? You see that it works quite well until, but however, even if you bring the order to infinity, right? Even if you take infinitely many derivatives, you see that it only converges to the actual the Taylor expanded function only converges until x equals to plus minus 1. Z Star made a very good video on this. So Z Star, he made a very good video on this. And the reason is because this function, it kind of, and this is known as the radius of convergence. This is known as the radius of convergence. And so the radius of convergence at x equals to 0, you can say that the radius of convergence is equals to 1, because you can only go distance 1 away from this point that you Taylor expand about before the Taylor expansion breaks down. And how do we tell the radius of convergence from looking at the function? We actually look at where it has poles. So in this case, it has poles at x equals minus 1 and plus 1. Okay, then and this case is very obvious. I mean, because you substitute these values into here, you see that the denominator is 0, it blows up. But what if I Taylor expand a function? Taylor expand a function like x squared plus 1. right? We can see that if we Taylor expand it around x equals to 0, we actually get radius of convergence. I'll just say RC equals to 1 as well. But it is a bit funny because doesn't it seem like there's no time, there's no point in which the denominator blows up, right? Along the red axis, there's no divergences. But why is the radius convergence still 1? If we go ahead and try, if we Taylor expand around x equals to 1, we see the radius of convergence is actually square root 2. So this tells us that this is a hint at us that actually, right, the poles of this function is at plus minus I. So if we look at the complex plane, right, this imaginary and this is real, we see that the poles are here. The poles of this function, the divergences are over here. So what we can learn from this example, Z Star, once again, he made this video exactly detailing this calculation. We can see that if we Taylor expand any function around a point, let's say over here, the radius of convergence is the distance to the closest pole. Okay, so far. And that means that the radius, that means that the Taylor expansion only works to some extent. But okay, so what's nice? What is analytic continuation? I'm not an expert in this area, but I know the principles around it, and it's very cool because if we have a function, right, and let's say there's some poles like this, perhaps poles are over here, then let's say what if we know the form of the function when it's Taylor expand around here? That means that we can actually let's say we know the function about this point, meaning we know the Taylor expansion about this point, but because of this pole over here, the dots are the poles. Okay, and this is the center of Taylor. Then we know the function up to this point, but what it means by analytic continuation is that if we want to find the function evaluated at this point, right, how do we do it? The answer is that we actually find the form of the function at, let's say, this point, and we do so by defining the function at this point such that it is compatible with the function at this point. So in some sense, but by Taylor expanding around this point, this new point, we see that we have a new radius of convergence. Right, a new radius of convergence. Yeah, question?
Okay, I think I can say what you're concisely saying. Basically, the idea is that you have to have the function has to be holomorphic. So you have to extend the function in the differentiable way.
Yeah,
That's
exactly. Yeah, so I extend the function in a way that is compatible within these two regions.
That's what compatible means.
Yeah, and then I can continue doing this until I reach everywhere, right? Everywhere I define it, and now I know the function at place. Yeah, I define the function over here in this region, but now I know the function over here, and that is what they mean by analytic continuation, where if you have this function, right, you see that it only works for some specific values, but if you it only works for, let's say, we know the value for s equals to 2, correct? But by analytic continuation, you can actually plug in any value of s, any complex value of s into this Riemann zeta function. And 3 Blue 1 Brown also made a video on this. Yeah. So if we search analytic continuation, it actually the diagrams will look something like what I've described so far. Yeah. So you see, in this case, it's a Riemann surface. So you actually analytic continue along the Riemann surface. Yeah, these are some ideas. Yeah. Okay. So I just wanted to take a small detour into it. Complex analysis is very fun to get into. Yeah.
Study group.
Study
group to do complex analysis.
Sure.
Oh.
Yeah, I'll be happy to talk about complex analysis.
We can talk about it after lesson.
Yeah. Okay, so let me just get a bit of water because my throat is a bit pain. So okay, even back to this question, right? We wanted to evaluate this integral. and Hadamard regularization allows us to assign a meaningful value to this integral, even though it has poles. So how do we assign a meaningful value to this, right? Okay, so the poles of the function, if we draw the function out, the poles are at plus minus ck, correct? This is the omega axis, and we integrate along the real line. So we go, we are running along the real line, right? And then we hit this pole, this part no problem, this part no problem. So there's that the Hadamard regularization basically tells us to go around the poles, but you see that there's a few different choices. We can go it on the upper way, or we can go on the lower way, right? This way we can make another independent choice, right? So there's a total of 2 times 2, which is 4 choices. In this particular slides, I go through the choice where we go above the poles in both cases, because that would give us something known as a retarded propagator. And this retarded Green's function, it would turn out to have the answer, the retarded Green's function would turn out to encode the physics that we want to, that makes sense, right? If we choose to go via the lower, go around the poles via the lower way, then we actually get essentially a propagator that tells us our sources can affect the past. Meaning that if I put a point charge over here, if I create a point charge, right, I will move a point charge around here, then this point charge, it actually creates an electric field that propagates back in time, which doesn't make sense physically. So the choice of the contour, right, if we try for all 4 of it out, it turns out that the choice over here is the one that is most sensible. It creates the most sensible physics. So I choose to go above the two, I chose to go above the 2 poles, and so this becomes the contour integral. Yeah, in contour integration, so contour integrals are basically line integrals in complex space. So if I have the complex plane, then I choose a contour that goes in a loop. The value of this contour integral will actually depend on, it turns out, right, by the residue theorem, that the value of this contour integral depends on the poles that's inside the contour. It doesn't depend on the value of poles outside, and you can actually choose any contour, and it only depends on the residues of these poles inside the contour, meaning that I can wobble, I can change the contour integral all I like, right? As long as it doesn't pass through any of these poles, the value doesn't change. So it's similar to topology, where you can morph the surface without any intersection, right? Likewise, this has some sense of topology to it. Yeah, in fact, the winding number in some model, right? Like the winding number, for example, in topological physics, you learn that the winding number in the SSH Schrieffer-Heeger model. I actually made a video on this where the winding number is given by a contour integral, and that means that in some sense, complex analysis is responsible for some topological physics. Yeah. So okay, the upshot of this is that I've chosen this contour, but it's quite a I can just as well, right? I can just as well say the contour was just a straight line, and I push down the poles a little bit. And this would be more convenient for our calculations, because if I wanted to do this contour integral around the pole, it can be done, but it's a bit inconvenient, because I'll need to break the integral up into this semicircle contour. So, but because we have this, because we are allowed to topologically morph the contours as long as it doesn't pass through the poles, right? These two pictures are actually equivalent. So I can push down the poles, and that means that I just need to evaluate this integral. And when I push down the poles, that actually amounts to, if we look over here, that actually amounts to, initially like omega squared, right? Over here, that actually amounts to changing this omega squared into omega plus I epsilon squared, because now yeah, in some sense, omega plus I epsilon, right, is actually pushing. So this is, if this is along the real axis, right, pushing omega plus, having omega plus I epsilon means that this is omega plus I epsilon, and then the poles are where they are originally. So okay, so this was the initial picture that we had. One way is to push the poles down. Another way is to equivalently is to push the entire contour integral up as well. So all these parts gets pushed up, and that's the integral that we're performing here. Yeah, in reality, all these would result in equivalent values for the integral. Okay, so I do this integral. So if I if I expand the denominator out, I can also check that that gives me the following expressions for, if I factorize the denominator, that I can see that that gives me these two values also. And you can see that that is roots at omega equals to ck minus I epsilon. Yeah, so this contour integral, how do I perform it? I'm going to denote it by I omega for brevity. And so when I want to perform this contour integral, there's two ways to close the integral. One is to close the, I have an integral along the real line. I have an integral along the real line, right? One way is to close it in the infinite semicircle above. Another way is to close it in the infinite semicircle below. Yeah, so it turns out that, which one do we choose? It turns out it depends on the value of t minus t prime. If t minus t prime, okay, so why do I want to close the integral in the first place? I want to close the integral because this line integral can be, this line integral which I want to find over here is equals to the contour integral, and I can evaluate the contour integral because I know that contour integrals only depend on the values, depend on the residues inside the contour, the poles in which it encircles. So contour integrals are easy to do because you can use residual theorem, and the semicircle one is actually going to be 0 by Jordan's lemma. So the reason why I want to do contour integrals, I turn this infinite integral, right, from along the real line into this contour integral minus the semicircle one. And the semicircle one is just 0, so actually it's just equivalent to the contour integral. So now, if I want to find integral along the real line, all it amounts to is finding the residues inside the contours. So how do I close the contour? It depends on the sign of t minus t prime. If t minus t prime is less than 0, right, then let me see. Yeah, if t minus t prime is less than 0, then we close it on the upper half plane. Okay, so if t minus t prime is less than 0, then I close the integral on the upper half plane. So I have this as my contour, and these are my two poles below the real axis. And if I close the integral on the upper plane, on the upper half plane, I don't encircle any poles, which means that the contour integral is 0 because inside this is a holomorphic. That there's no poles, which means that is yeah,
Completely continuous.
yeah. Holomorphic is essentially saying
Differential.
complex differentiable.
Oh, sorry.
Yeah. So I see that if t is less than t prime, right, then the value of my integral is 0. What if and that means the entire Green's function is actually 0. And that actually makes sense because what was t and t prime? If you go back to our definitions, t and t prime were t is the time, yeah, if I go back to my definitions, let me see, t prime damn mention t prime is the t prime is the past. Yeah, okay, t prime is the past because yeah, t prime is the sorry, t prime is not necessarily pass. The pass is only whether t is less than t prime or not. But t prime is the t prime is where the source comes from. So okay, I get it. It's over here. To be very clear, it's over here. Where's my integral? Yeah, okay, if it comes back to this equation, what is t prime and what is t? So if t is over here, is the one that we're solving for, right? In some sense, t is the current time. Whereas t prime, right, is over here. So I'm saying that the current, okay, if I look at this one, the current, when you go back to this equation, it tells us what t and t prime means. Okay, so t is the current time and t prime is the source time. So t prime is what we plug into h, and h is our source. And then we integrate over t prime, right? We integrate over basically, when we integrate over t prime, it just means that at this t prime equals to, let's say, 0, h has some value, and h has some value, and at t prime equals to 1, h has another value, and I want to sum up all these contributions weighted by the Green's function. Weighted by the Green's function. So the Green's function is kind of telling me, if I make a disturbance at this t prime time, at this time t prime, using the function h, right? I can define the function h as I want. Then how is this h going to affect? How is this h going to affect my f, right? And how it affects, right, is weighted by this g, and g takes in 4 parameters, right? It basically tells, g is basically a way to propagate information, right? Going back to the name, propagate information from my source to the function f, which is the electric field. So remember that h is our source and f is our field, right? F is our field, the physical quantity, the physics basically. So g tells me at for my h at prime time with position x prime and t prime, how does this information propagate to the measurement, to the field x and t at time x and at place x and time t. Yeah, so what this basically, t is the current time and t prime is the source. Okay, so what this means is that we got that in the case where t is less than t prime, if my current time is less than the source time, that means that the time I'm measuring this guy, right? I'm a guy here, and I have a stopwatch. I'm measuring at time 12 p.m., right? I measure the field strength phi. I measure the field strength f, right? X at time this one. And I'm saying that the t prime, the source, right, it actually comes after my measurement. Then certainly, right, t less than t prime, I don't want my future source to affect the past. If not, it violates causality. And so it makes sense that the Green's function is 0. Basically, because the Green's function is 0, it tells me that the future t prime cannot affect the past. Okay, the future t prime over here cannot affect the past. There's 0 weightage, right? 0 weightage. It does not propagate. Sources do not propagate information back in time. Okay, is that good? Any questions so far? Yeah. Okay. Yeah, I hope that I haven't lost any of you. Yeah. Okay. And then this decay argument over here, actually this decay argument is made precise using Jordan's lemma. But this decay argument is a way to see more intuitively why the semicircle contour integral gives 0, right? So there's 2 ways to show actually there's only one way, mathematically rigorously, there's only one way, which is Jordan's lemma. But the decay argument helps you do an intuition for Jordan's lemma. Okay, so that's for the t less than t prime case. What about the other case? If t is greater than t prime, then it turns out that the integral for omega is proportional to this. And we see that, and that means that actually, and we need to enclose we need to complete the contour via the lower half plane. And by going via the lower half plane, right, the semicircle contour integral is still 0, but the entire contour integral, it now picks up the residues of this integrand over here, this integrand being I omega. And this, if we calculate how do you find the residues at this point? We find this guy, Okay, we look at this guy first, right? We look at what values of it. Okay, so the residue of a function f of omega over omega minus a is equals to f of a. Yeah, roughly speaking, yes. Yeah. So this is how you find the residue of a function. So we look at the two values of omega that makes the denominator in infinity, and for each one of them we substitute that into the numerator, substitute omega equals to that value into this guy and into the other one also. So if we repeat that, we add the two residues together, then we get this, right? We can see that the complex conjugates. So okay, they are not complex conjugate, they're minus complex conjugate. So they pick up the I sign, 2I sign, right? And then yeah, and then that gives us this. So we know that integral over omega gives me this, right? The full Green's function, the retarded Green's function, the full retarded Green's function gives me this. And all that remains to do is just to do this integral in spherical coordinates. Remember, this is an integral over three coordinates. And if we do that, we actually obtain this expression. And this is nice, right? So this is very nice because, okay, so this is for the case where time t is greater than t prime, meaning that the source, right, it comes before the measurement, right? If the source comes before the measurement, then there's some effect on the measurement. So if I put it all together, we have this heavy side. This is called heavy side step function, heavy side step function, or heavy side theta function. And basically this value is 0 if t less than 0, is 1 if t is greater than 0. And at precisely 0, it is some people say it's half, but some people say it's half and some people say it's not defined. But I think to fully understand it, you need to go into the theory of distributions again, because these things basically only kind of make sense when you put them in integrals. Yeah, along with the delta, right, Dirac delta, it only makes sense when you put them in integrals. Basically, the theory of distributions is the upshot of theory of distributions is saying that functions, right, all the functions that you see, what are functions used for? All the functions that you see, right, they kind of implicitly live inside an integral sign. That's my current understanding of it. Yeah, but my understanding of it is not super rigorous as well. So okay, so we put together the full retarded Green's function of this form, and we see that this thing would be 0 if the t minus t prime is less than 0, and it is this thing if it's greater than 0. so we see that from complex analysis alone, right, and by a clever choice, by a good choice of the contour, right, in reality we pick all 4 choices and then we reject the ones that don't make physical sense. But for one of them, right, we actually have inferred quite a lot of things. We actually inferred that one is causality. Electromagnetism equations, the solution tells us that a source in the future cannot affect a measurement in the past. That comes in this form. Another thing is the potential. This is just the scalar. This is just it's just of the form 1 over r, right? And that essentially tells us that, yeah, it's just of the form 1 over r. And the last term over here is a Dirac delta, which means that the Dirac delta is only true. This thing is 0 except when t minus t prime minus x prime over c is equals to 0. And we rearrange this. This just tells us basically x equals to ct. The position, right? The difference in position, right? If my source was here, my source is x prime, and my measurement is x, then it will only see this potential value. It only see this potential value. One is if it's the time comes before, right? If my measurement times come after my source time, right? Another thing is it's only when x equals to ct, which means that I only see this potential when the essentially the information has traveled at the speed of light to my measurement location precisely at the time x equals to c. It's just distance equals to speed and time. So from complex analysis, we actually pick up from this retarded Green's function, we can actually see that there's all the features of physics built into it, and all this came from mathematical analysis. Yeah, and this is, generally speaking, this is what happens. This is when you study higher level E and M, right? Either higher undergrad or in grad school, E and M. EM, like Jackson E&M probably has quite an extensive analysis of this. We study antenna design. Antenna design is all about radiation field patterns. You come across quite a lot of these. Yeah. Okay, so Green's functions, we've gone through an extensive example of how Green's functions appear in electromagnetism, but it turns out to be they also appear in quantum field theory, along with any other field that basically requires you to solve a differential equation with some source term, right? Previously we saw the scalar field theory. We saw this, right? M squared, was it a plus? I think it was a plus. Equals to J. This thing, we need to find the inverse of this differential operator, which is given by the Green's function. So we're looking for Green's function that satisfies this. Yeah, x minus x prime. Yeah, so here's a table of Green's functions that you can check out, right? It shows the table of Green's function for quite a lot of operators. For basically homework, for your own calculations, right? It'd be good to derive it for this one, the Feynman propagator, is something that's going to come up when you do QED. So I didn't mention this earlier, but one hallmark, right, is QED. So I hope that in a few lessons time we can start to dissect all the parts of QED. And that will require us to understand quite a few concepts, including propagators, spinors, because QED fermions are spinors. Yeah. So the Yukawa potential and Feynman propagator is definitely a stepping stone towards QED. Okay, so it's one of the ingredients of QED. So it'd be good to take a good look at the Feynman propagator. Other than that, you can look at some, if you're looking for easier calculations, you can look at some of the harmonic oscillators. perhaps there are things that you're more comfortable with. Yeah. So okay, so back to QFT. So the other three choices for the contour will give us the advanced propagator and the Feynman propagator, and the last one will give us basically an inverse kind of Feynman propagator. So the Feynman advanced propagator basically tells you, so the retarded propagator tells you that your sources can only travel, your sources can only affect measurements that come after it, right? T must be greater than T prime. Right? T prime must be less than T. That's your retarded propagator. Your advanced propagator would be the other way. Your advanced propagator basically tells you that sources can only affect its path, which in this case doesn't make physical sense, so we will reject it as, even though it's a valid mathematical solution, right? It's a valid regularization of our integral, we reject it because yeah, we reject solutions that don't make physical sense. And then one of them will give us the Feynman propagator, which basically tells us that the Feynman propagator is a contour that looks like this. So we have our two poles. We have our two poles over here. And the Feynman propagator looks something like that. It goes over one of them, it goes below one of them. What it amounts to is that if T is less than T prime, right? Remember we closed it on top, right? Then we actually have just one pole. And if T is greater than T prime, then we close it below, then we have another pole. So what that means is that the Feynman propagator basically tells you that if I have a source term, it affects both the past and the future. And this seems crazy. So that's why I reject it for electrodynamics, because we know that electrodynamics, it only affects it in forward in time. However, right, when we actually do QFT, we actually use the Feynman propagator because one interpretation is that particles traveling forward in time, it can be seen as antiparticles traveling backward in time. Mathematically, is equivalent. So when we want to we only accept the retarded propagator because it ensures causality. But it turns out that when we talk about QFT in future, we're going to do calculations that look something like this. So we're going to say the fields become operators. We're going to say something like that. And we want this to be 0 if x and y are space-time. Each x and y is actually the time and the 3 space locations. Okay. And we want this to be 0 if x and y is space-like. And this commutator, right? When we substitute in the Feynman propagator into this commutator, turns out that the Feynman propagator is precisely what is needed for to cancel the amplitudes for particles for traveling forward and backward in time. So in QFT, we actually use the Feynman propagator. Yeah. So it's quite interesting. So okay, last part of why propagators. Yeah, this is one of the last few slides already. Last part on why propagators are useful, why they are cool, is because they are used in path integrals. Okay, they are used in path integrals. How so? This actually is going to lead us to the Feynman diagrams really soon. So, okay, so the path integral formalism is something that is not super, it's a very useful tool, but it's also kind of like a black box. We get ideas out of it, but none of it is fully rigorous because there's no well-defined measure for this dx, because you're actually trying to sum over all the paths. Mathematically there's no well-defined measure, and you actually get a lot of nonsensical results out of the path integral as well. Yeah, but it is useful as an idea generation tool. Okay, so path integral basically tells you that the amplitude for some process measure, you create a particle at some initial time and place, and you want to measure what's the probability that it goes to some final time and place. And this is actually given by the Feynman path integral, which means that initial time and initial position, final time and final position, you actually consider all paths, right? and all the wild kind of paths that you can create. For each one of them, you weight it with e to the I s, where s is the action of that path. And then that gives you your amplitude. One nice thing is that you see the h bar over here. In the limit that h bar goes to 0, which is basically the classical limit, right? In the limit where h bar goes to 0, you actually recover the classical theory that tells you you minimize the action through the stationary phase approximation. So the stationary phase approximation tells you that if you want this loosely speaking, right, it tells you that this thing, which is a phase, right, is quite chaotic, right? If I plot this in the Argand in the complex diagram, right, it perhaps for one path is like this, one path is like that, one path is like this, one path is like that. It basically is almost uniformly spread around the unit circle because there's so many paths, and basically if you sum up so many of them, almost all of it gives you 0. However, there's a case where if your path is stationary, right, it's kind of like if the s looks something like that, right? In the case where the path is stationary, so this is s of so the x-axis over here is the space of all paths, the space of all paths, and this s, right, is the action of a particular path. For when you have a path like that and a path like that, they are generally destructive interference. However, when you have a point with a particular path, right, which leads to a stationary action, which is precisely our principle of least action, right? When you have a path that leads to this specific path that leads to a stationary action, you see that it doesn't destructively interfere. So in the limit where h bar goes to 0, right, this path that leaves this path that causes the action to be stationary, right, meaning you perturb the path a little bit, the action doesn't change by much, right? That's the definition of a stationary path. This, in the limit that h bar goes to 0, you actually say that this guy actually gains huge importance, and basically he dominates this entire path integral, and that is and that is why you get the probability, and that is why stationary in classical mechanics it follows the path of least action. So in some sense, the Feynman path integral is a way to kind of think about the path of the stationary the path of least action principle, because if the path integral was the most physically fundamental object, then the principle of least action follows naturally from it, which will be quite a convincing argument for why the principle of least action is true. Okay, so QFT it feels quite natural in the path integral framework, at least for introductory stuff, right? Before we run into the issues. And Anthony Z's book, awesome book on QFT, he takes this path primarily. Yeah. So okay, so let's say we have our phi theory again. And this is the action. Yeah, so this is the action. So if we plug it into the path integral, we can integrate by parts. Actually, this is integrating by parts. This is just the equation of motion, right? This just gives you the equation of motion. Integrate by parts. If we integrate by parts, then this partial phi squared becomes partial squared phi, and then you have a phi over here. So phi partial squared phi. If we do this path integral, how do we do this path integral? It's very daunting because how do we integrate across all paths? But we can actually draw a very nice analogy with multivariate Gaussian integrals. In multivariate Gaussian integrals, you integrate over a lot of variables, and they have a form of QA. So A is a matrix over here. A is a is a n by n matrix, and Q is a column is a column of is n by 1 is a n by 1 column of all the coordinates Q1, Q2 all the way to Qn. So if you do the dot product, this is actually a quadratic form. It's basically quadratic in Q. So there's Q1, Q2, Q1, Q3, Q1, Q4, Q1, Q5, Q2, Q3, Q3, Q2, Q4, and so on. And also along with all the Q1 squared, Q2 squared, right? Any of the two, you and choose two. And then besides this, so that's what this term means. And then there's the JQ, which is just J1, Q1, J2, Q2, and so on. And it turns out if we do this multivariate calculus, multivariate Gaussian integral, you actually get this. We see that the Q has disappeared because they're integrated out, but the J, now that it's A inverse that acts on J, right? And then there's this determinant over here. So we see that when we have such an integrand, we get such a result. We need to get A to A inverse, right? If in this case, A was a matrix. So this, it amounts to, if we look at the path integral, right, it's quite similar. If we discretize our field phi, and this, we think of this as a linear operator on function space, then we just need to invert this differential operator. And we just saw precisely how to do that. We did it using Green's function. So if I denote dxy as the Green's function of this differential operator, then that is very nice because now my path integral, which I call z, right, is now given by this expression. So we had our j's, right? J's being the sources, and we have our A inverse over here, our Green's function. And okay, normalization condition. One reason why I call this z is because it actually has connections with the partition function. Soon we're going to learn that QFT has very deep connections with the statistical mechanics, statistical field theory. So Z actually is the path integral actually gives you the partition function after you do wake rotation. Yeah. So the normalization constant over here, right? The determinant, remember we saw something over determinant of A and then the whole thing like square root or something. That term turns out to be, this normalization constant turns out to be Z of J equals to 0 because it just amounts to when, if we look at, it's just equivalent to removing the J terms over here, because if we substitute J equals to 0 into here, right, then the path integral is just this, okay, and J equals to 0, and this J equals to, and this ZJ equals to 0, yeah, so if we move this to the other side, Zj over Zj equals to 0, this might look familiar because in statistical field theory you had something like that, and this in statistical field theory you had something like the probability of some microstate let's say psi is equals to the energy of that microstate over the summation of all that thing, right? This has very nice parallels with it. Yeah, and in statistical field theory, you can take from the partition function, can calculate almost every quantity. Essentially, the partition function, when you have calculated it, you have solved the theory. And likewise, right, in quantum field theory, when you have the partition function, you can actually derive a lot of calculations from it as well, such as correlation functions, by taking derivatives of this partition function. Okay, so we focus our attention on this Wj over here. We see that Wj is basically the exponential of, it is basically the integrand over here, right? So we see e to the I Wj, right? Wj being this thing. Wj is quadratic in J, right? Wj there's two powers, there's two J's appearing in it. However, e to the iwj, right? This thing has infinitely many powers. So if you expand it in Taylor, with 1 plus iw minus w squared over 2, and then you have plus you have minus I. Yeah. Basically, you expand it in greater and greater powers. Greater and greater powers in Taylor expansion. So you see that w cubed, right, that will have 6 powers of j and so on. So and we see that at the same time, right, this term gets smaller and smaller. So I didn't manage to include it in the slides in time, but in future where our if we put an interacting term into here, let's say lambda over 4 factorial phi to the 4, then our e to the iwj would have increasing powers. You see right now we're increasing powers of w, right? Our lambda will have increasing powers as well. So we'll be able to expand our partition function in terms of this increasing powers of lambda, and that gives us a perturbative expansion, and that will lead to Feynman diagrams. That's why, right, they say, you might have heard of terms like fifth order loop correction. It's because when they do the first order, right, in terms of interactions, when they do when it's just a single power, right, in 5-4 theory, there's this Feynman diagram, and that's pretty much it. Then we have phi squared, right? Then you start having so we know that propagators are the lines, right? And propagators are the lines. And what are the vertices? The vertices are actually interaction terms. The vertices are interaction terms. So if you have phi squared, right, that means there's two interaction terms in this for the phi squared. Sorry, for the lambda squared. That means there's two vertices. And so we are asking how many ways are there to arrange two vertices, and each vertex, right, must have, in this case for the 5-4 theory, right, you see that each lambda will come with phi to the 4, which means that each vertex must have four legs, four things attached to it. Oops, they say my internet connection is unstable. Do let me know if I'm laggy.
You're still good. You're still good.
Okay, great. So yeah, so that's something that we can look forward towards. Yeah, I wanted to try to include it, but I didn't really have much time. So okay, anyway, it's a bit late already. So for assignments, right, there's this common, there are two links over here. I forgot to put a new line over here. Actually, these are two separate links. I split them over here. This is one link, this is one link. Common integrals and quantum field theory. This is a very useful one to go through. Let me just roughly speak which ones are the ones that are more useful. Okay, so just now we saw that we have generations, Gaussian integrals, higher dimension. That would be something that you can convince yourself of at least once. Yeah, all the Gaussian integrals are nice to work through. Then we have yeah, those are Gaussian integrals like this. Then our Dirac delta integrals are also good to work through because they are used very extensively. Yeah, doing things in Fourier space, these are all useful. Coulomb potential, Yukawa potential, yeah. Yeah, these are all good. Yeah, okay. And also, as I said previously, the Green's function, table of Green's function, this is something that is nice to work through as well, especially for the Feynman propagator. Try to take a look at it. Yeah. And besides that, right, if you're less in the mood for calculations and more in the mood for just watching videos, Anthony Z's QFT book is very good. Actually, he talks in chapter up to chapter 1.7, he talks about Feynman diagrams. It'd be good to do some reading ahead because that's what we're going to talk about. I'm going to try to cover in the next lesson. Friedrich Schuller's Geometric Anatomy of Stereophysics is very good. The important ones are here, I've highlighted. Because I want to, if we're going to push towards QED, if we're going to push towards QED, we need to understand spinors, and spinors is best understood when we understand Lie groups, because spinors, when we talk about spinors, there's the Lie algebra, and the Lie spinors are basically representations of spinors are representation of the SU2 Lie algebra or Lie group. So it'll be very useful to it's indispensable, in fact, if you want to understand spinors, to understand representation theory. And representation theory or group theory needs us to know groups. And in physics, we use continuous groups, so you need to know Lie groups. Lie groups are groups. Group theory in math plus the Lie groups are manifolds as well. So Lie groups are manifolds as well. And I would say the manifold aspect is actually a bit more important because you talk about we talk about tangent space at the identity. If you know group theory, it will be if you know group theory, my impression is that from mathematical group theory, we talk more about the algebraic structure of it. Like you talk about the center of a group, you talk about representation of discrete groups and stuff. But in Lie algebra and Lie group, right, the more important aspect is actually understanding this correspondence. And to understand this correspondence, you must understand the tangent space. And to understand the tangent space, you must understand manifolds. So I would say that manifolds is actually the more important thing if you want to understand Lie groups. Because I actually didn't know a lot of group theory when I studied Lie groups. I just know when I studied the manifolds part, and minimal amounts of group theory, I understood Lie groups already. So to understand manifolds, right, it's important to watch Friedrich Schuller's lectures. In fact, I learned manifolds from him. There's also the Nakahara Geometric Anatomy of Physics. No, sorry. I'm getting names confused. Nakahara Geometry, Topology, and Physics. Yeah, Geometry, Topology, and Physics. This is also a good book that I've read. Okay, so I'll try to encourage you guys to understand and try to be able to explain roughly what each of these statements mean after watching Friedrich Schuller's lectures. Because if we don't touch representation theory, right, it's almost impossible to talk about spinors. And if we don't talk about spinors, it's almost impossible to talk about QED. So currently, if we want to talk about QED, we need to be able to, currently we're only talking about scalar fields phi, which is boring, right? We want to be able to talk about spinor fields. We're not talking about spinor fields, and to do so, we cannot get by without Lie algebra and Lie group representations. So I'll try to encourage you guys to do some of that. If not, something I didn't mention previously about canonical quantization is that remember I said that after finding the Fourier moods, right, you have A and A dagger of K and A of K, they turn into operators. We put the heads on top of them to mean that they turn into operators that act on some Fock space. That actually would turn the fields phi into operators as well. So basically QFT in canonical quantization, fields become operator valued. QFT is about operator valued fields. So we know in the potential function is a scalar field, right? Every point in space gives you a real number. The electric field E is a vector field. Every point in space gives you a vector, right? And in QFT, right, every point in space gives you a operator, an abstract operator, and the operator in the sense that if you guys don't know yet, right, look up QHO, ladder operator methods. There'll be some, the operator acts on the Hilbert space. Yeah, so if not, then I've more or less come to the end of my slides for this week. I think I'll try to have lessons every 2 weeks or so. So yeah, I'll try the lessons every 2 weeks because I need time to prepare the slides as well. So if not, that's all for today's lesson. Anyone has questions? If not, you guys are free to go. Yeah.
I'm just gonna ask a bunch of math questions. So if anyone wants to like sit in math, listen to.
Okay, thanks, Sam. Yeah. Okay, I hope you guys enjoyed. Yeah, I'll try to. Honestly, I mean, I talked for very long, but the best way to learn QFT is to try to do the calculations. And for this week's homework of sorts, right? I encourage you to try to do the Feynman propagator, try to find the contour integral for the Feynman propagator and try to understand it. And the whole point of me here also is that whatever questions that you guys run into, I want to be able to help answer them. Yeah. Because I think the greatest difficulty is when you have to study something and then when you're stuck, you don't have anyone to ask. Yeah. I felt almost, I kind of felt that way when I studied QFT. So I hope to get rid of that hurdle when you guys learn QFT. Yeah, but without going through the calculations yourself, you really won't be able to get a sense of QFT. Yeah. So yeah, so I really encourage you guys to do the calculations, as annoying as I find it also. I mean, I wish that physics was as easy as just learning the ideas without doing calculations, but it's only when you do calculations that you really are able to do it. Yeah. So for now, let's try in these 2 weeks, try to calculate the Feynman propagator, right, and understand the contour integrals. Yeah. Okay. Yeah. Yeah. Thanks, guys.
Thank you, Ching-Hao.
No problem. See you.
Thank you.
Thank you. Yeah.
Okay. If everyone's gonna wanna like can you go back to the slide for the homomorphism bit? Sorry, not the homomorphism, the one with
sure.
the Green's function. Yeah.
Press stop the recording.
I mean, like if you want, we don't have to. It's a
Yeah.
don't know if this is necessarily relevant because I was like, I saw kernel. I was like thinking, like, is that actually going to be a